¿Un dedo? ¿Solo sirve el dedo atrás? Derecho. Wow.
Prueba que funcione bien. Ya. So I think we can start with our seminar. Today it's a pleasure to introduce my friend, Tomas Fuentes, who is a PhD student here at USM. He also did his bachelor in astrophysics degree here. So about yourself, I think he enjoys a lot the financial market studies and cryptocurrencies. You enjoy play with your friends, making freestyle. What else? I think you also enjoy reading books. And yeah, it's nice about your topic, which is really, really interesting about the developing photometric methods for the detection of truncated dips in galaxies. And please go ahead, the scenario is yours.
Thanks for your presentation, Ignacio.
And let's do that.
My friend. So, yeah, today I will present you my method. I'm developing a method. So to start, I need to put in context the galaxy evolution process. In the color magnitude diagram, we have three regions here. We have blue cloud, green valley, and red circle. For blue cloud, we have the galaxies with blue colors and high star formation activity. Then we have a transition part called green valley, and finally the red passive galaxies are situated in the red sequence. My main message here is we can connect the color of the galaxy with the content of the stellar population. So if we have some blue colors, we can trace young stellar population, and for the red color, we have all the stellar population. Obviously, we need to take into consideration some degeneracy for the metallicity or the extension of the dust. And we expect that the galaxy evolved from the blue cloud to the red circle, and the process when they lost the star formation activity, we call quench. We have different types of quenching mechanisms in the universe. In the literature, we separate in two ways, like mass-driven and environment-driven. Mass-driven, we say for any internal process who affect that galaxy. For example, the proper stellar population evolution, the AGN for high stellar masses galaxies, or supernova feedback for low stellar masses galaxy, or the proper evolution, and then the environmental process or any external process who affect that galaxy. For example, the mergers, minor mergers, major mergers, or any hydrodynamical effects like ground pressure stripping. When the galaxy falling into the cluster, they lost the gas in the outskirts. But the quenching mechanisms are not independent, maybe are occurring at the same time. And it's really useful understanding the Penn plot published in 2020 to understand what happened with different sizes of galaxies and where the galaxies are situated. In the y-axis, we have the overdensity, tracing the environment effect, and the low mass in the x-axis, like the size of the galaxy. And finally, in the color bar, we have the red fraction. To understand this plot is really useful, fix any edge. For example, for low or dwarf galaxy, we have different colors in different environments. We have dwarf galaxy, blue dwarf galaxy, and red dwarf galaxy, but situated in high dense environments. Then, for example, for high stellar masses galaxy, all the galaxies are red, independent of the environment. Or if you are situated in a high dense environment like cluster or supercluster, all the galaxies are red. And this is how we understand the quenching mechanisms with different sizes. And this creates a standard model of the evolution of the galaxy. We expect that the galaxy first create the bulge and then the outskirts that create inside out quenching. So we expect that the red colors are in the center and then the blue ones in the outskirts. So we expect that the quenching following this process. And the inside out quenching create negative color gradients if we study radial the galaxy. We expect negative color gradients. Here, two cases, a study with Leo and Cooper in 2022, where blue galaxies and red galaxies, as you can see, both have the negative color gradients for E minus R or R minus C. This is really useful because we can study with color gradients the content stellar population, we can study the metallicity and the dust section. But are found anomaly galaxies called breakbill. Breakbill is acronyms. Their name is break bulge inside red disk. These are samples of a spiral galaxy presented by Tuttle and Tonensen in 2020. It's really interesting how they measure this galaxy. They measure the star formation activity in the center using a spectral index. And the disks are selected with the decomposition between the bulge and the disk and select optical red colors. And it's really interesting because this type of galaxy are noisier and found in all environments. And the morphology that the breakbill are is obviously red bulge, but break bulge with a truncated star forming disk and then optical red disk quench color. And that is my object that I want to looking for. And we don't have a consensus yet that how this galaxy are formed. Our best candidate is pressure stripping. When the galaxy falling into the cluster, lost in the outskirts the cold gas reservoirs and create a truncated disk. But in the case of breakbill are found in all the environments. So only case of breakbill could be run pressure. Another one is mergers or tidal interactions. A possible merger who any blue galaxy falls directly into the center in a red passive galaxy, possible create truncated disks. Some bars instability in the secular motion with the angular momentum could drive the cold gas into the center, or finally could off the gas accretion. Any process that we don't understand yet, maybe could off the gas accretion created a truncated star forming disk. But I can say we don't have a consensus yet what happened with this type of galaxy.
So if I understand correctly, and they are in all environment, I like the one on the right best because that's independent of the environment, right?
What?
Like the one on the right is just the galaxy itself. The merger and the ramp pressure need environment.
Yeah.
So, but this is probably not the result, right?
Yeah, definitely.
It's probably more complicated.
Yeah, because the TEM is connected with the environment.
Ah, okay.
The circumgalactic medium.
Yeah, exactly.
So we have different quenching mechanisms. We don't have a consensus. And then how I can search this galaxy? First, we need to understand the spectroscopy have a bottleneck. The detection requires spectral data, and these have some limitations. The first one is the observational cost because we need long exposure times. Then you are biasing your selection because if you only select the high luminosity galaxy, you are biasing in the stellar masses. And finally, the combination of both create a small number of statistics. For example, the Breakbill galaxy is around 100 galaxies. Then, our solution is come back to the photometry using Hyper Suprime-Cam because we have a good and better space resolution to detect the galaxy morphology. Previous work are created with using SDSS, but we propose using with Hyper Suprime-Cam. As you can see, the clearly difference between the resolution of the images. And here I want to explain to you what I'm looking for. For example, here we have a bulge clearly, but we have a spiral structure inside in a quench disk. Here too, we have a clearly blue region inside a red disk. This is really beautiful because we have a high truncated star forming disk, but inside a red disk. And finally, this is the opposite behavior. We have a short or really truncated disk. That are the objects I'm looking. How I'm creating automatic detection pipeline. My goal is take the raw data for Hyper Suprime-Cam and create the color diagnostics and analysis. And here, I will start with geometric characterization, extract all the useful information of the galaxy, effective radial, isophoto, color, magnitude, and angles, all the information. Then I need to correct the filters because we have red and green filters, or any filter that you want in Hyper Suprime-Cam, but different filters have different dispersion of light. So to trust in the color maps, I need to correct with the point spread function with kernels, a cross convolution with kernels, and finally create a color maps and color gradient and the respective criteria to found this object. That is my process, and this is where I'm situated now. How I can test the method in my undergraduate thesis, I'm looking this type of object using visual inspection in Hyper Suprime-Cam data. These data are extracted for looking for jellyfish galaxies, but in the way Rory and Ignacio found this type of object that is really interesting. This data is Hyper Suprime-Cam plus X-ray catalogs with some cut in the redshift and the mass cost, and I create a visual inspection looking for this object, and now it's like my golden sample to train my method.
How many did you have of those in the book? 154.
Yeah. And the previous work is really useful to understand how we can create high resolution images to resolve the galaxy morphology. And we conclude that this is a combination for 3 parameters. First, the redshift range, like the deep distance of the galaxy. Then the stellar masses, like the size or the brightness of the galaxy is connected. And finally, the resolution and the size of the galaxy, where this research was started. We cut it using the ground radius over than 2 arcsecs. And if we have the combination of three parameters, we can extract quality and good images to understand the morphology. There are some previews and preliminary results. They are really beautiful color map of my golden sample. For example, here we have the color for each pixel in the galaxies. And we can see inner region with the star formation activity with blue colors. Here too, this is the best one candidate with high values in the center and with blue colors. Or for example, here we are looking for asymmetries too. This is not homogeneous, we have a clearly preference here. And to contrast, I'm showing you how looks the outside in evolution and inside out evolution. This is the normal or standard evolution that we expect, bulge red in the blue colors, and here we have blue colors in red disc. They are the clearly difference between the samples. And finally, my physical analysis. First, I want to.
Do you also find these asymmetries in the ones in the left, in the right, sorry?
Yeah.
These asymmetries that you find there, do you also find them in the ones that evolve from inside out?
Huh?
In the ones in the right.
This one?
Also, in the right. Those, yes. Do you also find in those cases asymmetries? Like you find in the ones in the left? You are telling us that you are finding these asymmetries in blue.
No estoy entendiendo.
En la imagen de la izquierda,
Yeah.
abajo, nos estás mostrando que hay como unas asimetrías en azul. Solo te consulto si encuentran asimetrías igual, pero en rojo, en las que evolucionan al revés.
La verdad.
Están en ignorancia en el tema cuando trabajo en galaxias.
Yeah.
No sé si se encuentran en esos casos.
Buena pregunta. La verdad no estoy seguro porque estoy interesado en estudiar estas. Aparecieron como error, pero lo que sí sé.
El primer ejemplo de la izquierda, tú ves que. No, el de la derecha. El azul de arriba. La más izquierda es ese. Tú ves que parece un arco que está más rojo.
Sí.
Sí, ok.
Incluso podría ser.
Pueden encontrar.
Yo creo que puede darse.
Pero yo creo ¿Debería ser menos, Ignacio? Corrígeme, porque
Es que
los
las-
bienes espirales también deberían tener formación espiral o no
Sí.
están conectados.
Y tengo entendido que el gas frío es más sensible a cualquier proceso hidrodinámico, entonces sí se traslada el gas frío. Entonces el rojo se ve como consecuencia de que no hay azul.
O sea,
Yo creo
igual
que sí
puedes
van a
tener
ser-
como barras, ¿no? Como tener una parte roja que quizás tenga esa, digamos, región más extendida, pero claro, en esos ejemplos el bulbo es bien compacto, ¿no? Pero puedes tener una, de hecho, la perturbación en la barra es un mecanismo, entonces tampoco podría ser tan anómalo ese tipo de objetos desde mi punto de vista.
Sí. Vale. Then the physical analysis using the color maps. This is all the color maps because look different. We can study the size of the star forming disk, and my goal is understanding the color gradient between the end of the star forming disk and the end of the galaxy. Something like this. Extract a ratio parameter between the blue radius and effective radius to create my method. The size of the star forming disk is directly connected with key information. For example, the cold gas reserve, the asymmetry study, we can study symmetrical or asymmetrical. If we have a symmetrical candidate, maybe we're working with relaxed galaxy, any no symmetrical is affected, and possible is connected with the edge of the star formation. In the disk, really truncated, possible with the old stage, and not truncated is a possible young stage. And here I put in the cartoon of the combination of different sizes of the star forming disk. Here clearly we have a high size, and then here are really truncated, and we can expect that is connected with the star formation activity. Then the color gradient studies. I can extract color gradients in the radial data to fit CD fitting and understanding the content stellar population here, because I want to study the color gradient with the content stellar population to understand the age of the truncated star forming disk and understand which process is affected, because different ages are connected with different physical processes. Then Fourier mode, the last year in the galaxy evolution course, I test the Fourier mode for simulation for my observation data, taking some corrections, and we can conclude that it's really useful to detect bars, asymmetries, or lopsided galaxies. So for when I create a sample, I can apply Fourier mode for distinct the galaxy are created by bars or any lopsided process. And finally, for the last year, because now I don't know nothing about simulation, using simulation. Because I create a new criteria to look in these galaxies in simulation. Brainfield analogs are founded in Illustrious TNG, and the simulation is really useful to trace during the cosmic time the evolution of the galaxy. So my take-home message is, I'm developing the photometric method to find the truncated star forming disk, color maps, color gradient, radius. Then I want to apply to Hyper Suprime-Cam entry footprint to create a statistical significant sample. And finally, study the physical process, environment, time scale, using simulation, observation, and that's my work. Thank you for your attention.
Thanks everybody for the attention. So I would like to know if any of you has questions for Thomas, the students. You? No?
Yeah, I have a question about the data. Because do you, for the training, do you have, for example, the inclination for, like the inclination of the galaxy with respect to the cluster center, maybe? Like, are you considering the position or the position of the galaxy?
Yeah. First, for this data, we have some possible data of the radius in the clusters, because are founded in clusters. But for the new data, where I run all the process in Hyper Suprime-Cam, maybe some galaxies are situated in other environment, in isolated environment, and then I can do nothing with respect to the distance. But for this sample, I have some correlation between the cluster data, and for example, Ignacio created a paper from which properties of the clusters affect integration of jellyfish galaxy, and maybe we can reproduce the methodology for the same one, but with truncated disk.
And do you expect to see differences between the galaxies in clusters or outside?
Definitely. We expect that the main process is from pressure stripping, but we need to trust or confirm what happened in the part of the universe. But we expect that in the cluster are more.
Yeah.
Definitely. Yes.
And you said in the simulations you will use your similar detection method, but in the simulations, and you know in the simulations already that they appear.
Yeah. Because
And did you check like one to go back? I mean, I would be curious immediately if they are known in simulation. I would go. I mean, I don't know if it's that easy, but I would check how did this one, like with 5 at least, I would check where are they and how do they form.
definitely breakbeard are found in simulations. We have a paper with circumgalactic medium and the escape time of the breakbeard state, and they conclude that it's a short period in the galaxy evolution, like lower than mega years.
So there are few.
Yeah, and 2% of the galaxy are found
Okay. And then where are they in the simulations?
in all environments.
This is where they are all environments. Okay.
Yeah.
So, but this then means in the observations you should also see them in all environments. But maybe you see different types in different environments.
Yeah.
Or different radii or something like that.
Yeah, definitely. And we know that the first paper of breakbeard unbiasing because using only spectral data.
Yeah, okay.
Here we found, for example, here is a really beautiful candidate, a beautiful plot. Here we have the breakbeard in green, a simulated breakbeard in blue, and my candidates in red. Here the breakbeard have like a cut upper than 10 to 10, but I found in all ranges stellar masses. So we can expand the data of the stellar galaxy.
Question? I have a question.
Yeah.
So you have different drivers that could make this morphology appears. And the question is, how could, based on your methodology, split or separate the mechanism drivers? Because you are using photometrics, right? So
yeah, really good. It's a combination between the color gradients, because different quench mechanisms create different steeper in the color gradients, and then the Fourier mode is really useful to understand what happened in the structure of the galaxy. It's a combination between both the color gradients and Fourier modes.
Another final question, maybe?
Yeah.
I have the last one. Maybe thinking in the surveys here in Chile, how do you think can be like extended this kind of studies?
If the data works, definitely we want to apply to better mobility the method, because we are creating methods to create color blends with the photometry. We're not using software panels, so we can apply to new data in Chile. And see.
Excellent. Beautiful. So let's give us an applause again. Muy bien, muy bien. Me gustó.
El año pasado. Sí. Sí, ya está probado.
¿Tienes oficinas? Debería. Tienes que desarrollar. Bueno, el departamento está organizando, pero
Si quedan oficinas, otra pregunta.
yo creo que está generando, hay una red de estructuración, pero bueno, no sé cuánto. Yo creo que como último por lo menos error y eso también ellos deberían igual estar lejos, deberían estar hablando cada rato, lo van a hacer, debería ser, si están en la misma línea, está más eficiente.
La casa es una mentira.
No,
Es una mentira.
eso visa igual.
No, ahorita está la
Sí, güey, como, no he hecho mucho tema, pero siento que yo tengo entendido que la galaxia no tiene una forma. Pero no ese tipo de observación. Uno cambia eso. Sí.
Ahí directamente no podemos resolverla.
Como no la puedo resolver.
No puedo resolverla. De hecho, tengo una galaxia como en muestra que es literalmente una línea con una barra azul en medio. Y es como posiblemente podría ser algo así, pero no podemos hacer nada al respecto como para desinclinarla.
Exacto, había una probabilidad.
Veamos qué hay. Estas son unas cuantas, pero
sí.
No, todas están como muy hechas con. Y de hecho, por ejemplo, en el paper de las breakbits originales, trabajan con un radio entre semi-eje mayor y menor para poder trabajar solo con galaxias.
Sí, es como uno de los lineantes.
Sí, porque si no, no puede resolver la morfología de la galaxia.
¿Qué tan probable es que pase eso de campo?
Eso igual afecta ahora que lo pienso en la estadística.
Sí, pero que no hay un alineamiento preferencial.
Claro, es igual para la inclinación.
O sea, bueno, realmente sí existen alineamientos preferenciales dependiendo del ambiente y cosas así. Pero el universo, al ser tan grande y homogéneo en todos los sentidos, que al fin y al cabo se promedian las direcciones. Claro.
Tampoco se puede lograr como hacer como un tipo de modelo en el que se vea directamente.
Mira, yo para esta cosa del Fourier Mode, esta vaina es para simulaciones. Entonces, cuando no es luz, son partículas de masa que brillan, súper chistoso las simulaciones, pero tuve que desinclinar mi galaxia. Si la tenía como un poquito así, yo la forzaba a que sea así. Y era asumiendo los radios de, por ejemplo, si tenía una elipse, la elipse la circularizaba, como transformar el radio. Pero eso es asumir que sabe la inclinación y puede asumir errores. Pero para el Fourier Mode tengo que hacer eso. O en su defecto usar solo galaxias fake.
Y claro, eso que una galaxia una línea que sea azul, o sea, significa que todo como el edge sea la pura galaxia azul, digamos.
Estoy pensando. Sí, buena pregunta.
Yo
quiero estudiar la inclinación.
Igual me pregunto así como respecto a la inclinación, por ejemplo, la inclinación está conectada con la cinemática de la galaxia, o sea, entre mejor tu inclinación, en este caso si tú lo ves así, mejor va a ser la capacidad resolutiva de la velocidad de la galaxia. Entonces me pregunto, ¿tendrá eso un rol quizás en la dinámica o cómo es el momento angular de este tipo de galaxias? Porque las barras están relacionadas a eso. ¿Qué sabes que es así?
Lo que sé es que el medio circungaláctico en las simulaciones es de bajo momento angular. Que puede significar que tenga baja masa o que esté rotando lento, ¿cachai?
Claro.
Y puede ser.
¿Están en dónde? Tienen baja masa.
El Circungalactic Medium de las Breakers simuladas tienen bajo momento angular.
¿Y la masa de esas galaxias sobre 10 a la 10?
Sobre 10 a la 10.
Allá.
Entonces es como que lo apretó, ¿cachai?
Pero tienen baja velocidad simulada porque ya notan que es a propósito para estudiarlas mejor o es porque así de la simulación.
No, así es la simulación.
¿Y tienen barras?
El 30%.
De esas galaxias.
Sí.
Y rotan lento.
Y rotan lento. Por ahí vamos, sí.
Interesante.
Y ahí
que lo que pasa es que, claro, por el pressure stripping puede ser uno, el cúmulo, pero lo que sucede afuera igual.
No.
Pero claro, pues las barras igual tienen que ver con los mergers.
Sí.
Una de dos, ¿está como codificado en el ADN de la galaxia o está ligado al historial de mergers? Entonces igual sería interesante ver
por
eso
eso
en
las simulaciones te puede dar eso.
Claro.
Muchas gracias.
Vale,
muchas gracias por
Estuvo bueno.
Buena, Paco.
Buena charla.
Gracias.
Sí, estuvo buena.
Ahora tengo que trabajar nomás, pues. Ahora tengo que hacerla.
Sí, los gradientes de edad, cosas igual son bien interesantes.
Me toca leer cómo organizar la presentación.
Las
slides. No me sé entender.
de comunicación científica.
Sí, ¿no?
Se nota, se nota.
Eso es todo acá al final. Hay como que...
Es como, cabrón, esta es la weá que estoy haciendo. Quédense con eso. Y una cosa que aprendí igual de los profes, el thank for your attention no va. O si es que va, déjalo en una weá que te sirva, porque ¿cachai? No en una slide. Ahí ya la próxima pregunta.
A ver, está bien, está bien.
¿Qué pasa con los blending? Ahí están los blending. Sí, gracias chiquillo.
Estuvo bien, estuvo
Igual
bien.
me trabé en una, como que se me apagó el cerebro, fue como, ya, tómate la pausa. Es lo mejor que podía hacer. Ya,
Sí, es
volver al
que,
presente.
claro, a veces,
No se notó.
no, sí se entendió bien,
Bien.
se entendió bien.
Qué loco lo trabajable que es la comunicación en la ciencia. Es como,
Sí.
porque podéis mejorar esto, mejorar.
Es que yo creo que lo que es difícil es comunicar todo lo que uno debiera decir en una
Claro.
charla, o sea, como decir todo, tenerlo todo como súper ahí, vale, es bien, ¿cómo decirlo?
Estamos siendo grabados.
Es como harta información, entonces siempre igual es complejo estructurar todo eso.
Se puede
Pero,
hablar todo.
claro, pues eso.
Hoy esta no me dio, esta fotometría no me
Sí.
gustó, este día me sentía mal, me dolía la patita. Sí, eso es para los reportes de tesis, pues, güey.
Claro.
Pero no para un
Hoy
charla.
voy a ir a buscar a Daniel.
¿Va a almorzar usted?
Sí, 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 sí.
¿Ah?
Voy a buscar a Daniel.
Con esa.
Sí, pues sí, es mi trabajo. Gracias por el agüita, Ignacio Quirox.
Bro.
Y por la presentación.
Final improvisé, perdón.
Sí, güey. Trade financial markets.
¿Qué vas a comer?
Tendré que ir a buscarme algo, güey.
Podríamos almorzar.
Quiero comprar algo.
Sí.
¿Y qué tal?
¿Dónde la tía?
Sí, igual te puedo decir.
Voy a dejar mi cosa arriba y...
¿Y vas a almorzar?
Pero la que hay la pieza. Es que fue como. Ya, voy a ser honesto, me jugué un LOL dudoso. Tipo, cuando terminé, con coche tu madre, me tengo que bañar.
¿Pero en la mañana?
Sí, me desperté a las 10.